Right, this is the 8th video in the Algebra Foundation section. This is on functions. We're talking about composite and inverse functions and generally function notation, something you covered at a previous level, but we're going to reprise it here and maybe just look at it in a little bit more depth. So let's first of all, let's just think about this thing here, y equals x squared plus 3x. So you could draw a graph of this, couldn't you? And what we're saying is that y is the result of putting some value into here, so some value into this function x. So we can choose value, pop it in there, do our calculations, and we get our value for y. Now that function can also be written as we would call this the function here, but we can denote it here by y of x, okay, y brackets x, and what that sort of leads us to is that if we want to evaluate this function at x equals 2, then this is how we would annotate it. Y brackets 2, and then of course that will be 2 squared plus 3 times 2. That's going to give us 10. Okay, so so that that is basically the first stage, if you like, of looking at function notation. Question is, what would we mean if we wrote this y of 2x? Well, what we've done here is with this 2, we've substituted in for every occurrence of x in our function here. So if we follow the same idea and we just substitute 2x in there, then this is what we're going to get. We've got 2x there instead of x, and 2x here instead of x. And if we simplify that, we get this thing here, 4x squared plus 6x. But let's just think about this. This 2x here, I mean, essentially, it is just another function. All right, very simple one, but a function nonetheless. And if we were to call that function z of x, then you can see what we've actually done there is, instead of 2x, we can write this as z of x. So what we've got is y of z of x is equal to, well, once it's expanded and simplified, 4x squared plus 6x. So this combination here is a composite function. Okay, so it's kind of simple as that, really. Now we don't have to use y and z. I mean, it helps just to illustrate it at that stage, but I mean, they're only letters at the end of the day, and very often when we're talking about functions, we tend to use f. If we need another one, we tend to use g. There's other kind of notations and systems, if you like, but f and g, is quite common. So if we think of another example here, where f of x is 2x plus 5 and g of x is 3x plus 1. So if we put these two together, then what we're saying is that f of g of x is, well, we're going to substitute g of x, i.e. 3x plus 1, into here. Okay, so that's the crucial point, because instead of x, we're putting in g of x, and g of x is this. So our 2x plus 5 becomes 2 into 3x plus 1 plus 5. Okay, now when we write this, we tend to miss out this set of parentheses. Just write it like this, f g x, and that is a composite function. So let's just have a look at this as if, in a sort of process diagram. We've got x going into this function here, 3x plus 1, so multiplying the value by 3 and adding 1, and what we get out is g of x. And then we're putting that into this function, which is 2x plus 5. Well, our x is actually this g of x here. And so what we're getting out is, we would denote as f of g of x there. So if g of x is 3x plus 1, as we've said over here, and f of x is 2x plus 5, then our composite function, when we simplify it, is going to give us 6x plus 7. We should note, by the way, that f of g of x is not generally the same as g of f of x. It's you would expect them normally to be different, although on occasions they may turn out to be the same thing. But generally speaking, you can't assume that they're the same. So the order does matter. Right. Okay. Let's have a look. What else have we got? Right. Well, you may well ask, why do we need to write functions? What, if we know it's x squared plus 3x or 2x plus 1 or whatever, why do we need to write it as f of x? Well, as we go through and do sort of more advanced levels of maths, we actually find that we are actually doing maths on the actual function. So there's a lot of rules that we use to do with functions, which are regardless of what the actual function is, and we'll come to examples of those. But one of them, I think, one of the most important things from this stage is the inverse function. So if we look, what do we mean by the inverse function? So if f of x takes some value x, take a value of x and put it into f of x, and that converts it to a value, and the value we can say is the value of f. And then we've got some other function g that takes the resultant value and converts it back to the original value of x. Okay, so we go one way and then back to the same value. Then g would be known as the inverse function of f. So it's just reversing the process. So if f of x is going to be 2x plus 5, and then g of x would be x minus 5 divided by 2. I'll get to why I know it's that. So g of 9 would therefore be 9 minus 5 divided by 2, which is 2. And then f of 2 would be 2 times 2 plus 5, which is 9. So if we're looking at f of g of 9, okay, that's f of 2, and f of 2 is 9. So f of g of 9 is equal to 9. So we've taken our input here, and that what we've got as a result of this composite function is the same thing out the other end. So if we look at what we've done here, this is our 2x plus 5. Okay, so our x, we poke this function x minus 5 divided by 2 into here. So we've taken this and popped it into there. So that makes it a composite function. And if we just work this through, see the 2's cancel, and then the 5's will cancel out as well, and we're just going to be left with x. So f of g of x equals x. So the g is the inverse of f, and similarly, f is the inverse of g. Okay, yin and yang. We normally write the inverse function as f minus 1, though. So, well, let's just look at this example here. So these are the same numbers here. Let's just put it in graphically. X goes into our f here, produces f of x, and then we're going to divide, and then we're going to put that number into x minus 5 over 2. Okay, and so this process that we've gone through is we're taking the inverse function of something that's come out of f. So we would denote that as f minus 1, f of x, and that's going to be equal to x. So this actually is the other way around to this, isn't it? We just illustrated it the other way around. And how do we find the inverse? Well, one way of doing that would be, if we have a simple enough function, what we can do is we can look at the what we've done to Rx in the first function. In this case, we've multiplied it by 2, added 5. What we do is we do the opposite things in the reverse order. So we subtract 5 and divide by 2, and that's what we've got here. And that's why these two are inverse functions. Now, it's not always easy or straightforward to do that. It's nice and simple in this situation, but there's another way of doing it, which we will show later. So when we're talking about why do we need to write functions as f of x, I mean, here is one rule, and this is a pretty straightforward rule, but what we're saying is that the inverse function of the function of x is equal to x. And that is something that's true for, well, essentially for all functions, with some constraints in there, but it's essentially true for all functions. Okay, so that's what we mean by that. Right, now, just going to one or two other things. I think it's worth noting that the inverse of a function can be expressed graphically as its reflection in the line y equals x. So here we go. Here's a function. Here's its inverse. So these two are inverses of each other. This is the line y equals x, and we can see that one is the reflection of the other. Well, why is that? Well, in some senses, what we're doing really is just swapping the variables over. So a function which takes us from 1 on this axis up to what would that be? 2.75 here. Okay, so that would be the blue one. And if we wanted to do it the other way around, we could take our 2.75, and that would map us back onto the original value of 1. So we're kind of just switching the variables around, and that's why we have this property of reflecting in y equals x. We talk about the domain and the range. The domain is basically the set of possible values of x. You can see with this particular function, then we can't have negative x's. It's asymptotes down to this vertical axis here. So the domain would be all the positive numbers, and similarly the range would be the set of numbers that we're mapping to, that we're going to. So when we think about the function and the inverse function, the domain for one is the range for the other, and vice versa, of course. So that's something that will come up. So the idea of functions is very important in maths. It comes up more and more as you go into more advanced maths. I think you can probably think of your career in maths being a little bit like this. In the early years, we're basically bothered about numbers, aren't we? We're dealing with numbers and operations on numbers, and then as we get more advanced, then we start using variables, and our maths and our processes and our methods and everything tend to be with variables. X, for instance. And then as we progress, then what we're interested in is how functions perform. And so we have lots of rules and equations that govern how functions perform, regardless of what the function is. So this is something to watch out for as we progress. We see this in things like transformation of graphs. Where if we have a function f of x which has a curve like this, let's say, and then we evaluate f of x minus 2, for instance. So we're actually substituting x minus 2 in for all our x's in the function. Then what we find is that we've shifted this red line, in this case, 2 units to the right. So that's how that works. Okay, let's have a look at an example then, shall we? Okay, f and g are defined as follows. F of x equals a half into 4x minus 3, and g of x equals a half x plus 3/4, 0.5 and 0.75. Find f of g of x. Okay, so what we're looking for is f of g of x is 0.5x plus 0.75. Okay, and f is this half into 4x minus 3. So what we're looking at is a half into 4 into this lot, 0.5x plus 0.75. Okay, and then minus 3, which is here. Right, so we can work this through, and this is going to be 1/2 of 4 times 0.5x is going to be 2x. 4 times 0.75 is going to be 1.5. That's 3, and that's and then we've got our minus 3. So we can do the 3's cancel. The half cancels with the 2. That's going to give us x. Okay, so f of g of x equals x. F of g of x equals x. Now then, well, so let's just work it through and then see, this is not b but a. Right, we're going to do it the other way around now. So we want g of f of x. So we're looking for g of f of x being this thing here. And then, of course, our g is this. So our what we've got is 0.5. And our f of x is this bit here. So we've got 5 into 1/2 into 4x minus 3. Okay, and then we've got plus our 0.75 on at the end. So where does that leave us? So we've now got 0.5 into 2x minus 3/2. I'm going to call that 3/2 1.5 plus our 0.75. Right, so we'll just work that through. So that's going to be x minus, well, it is going to be half of 2x minus 0.75. Yeah. Plus our 0.75. Well, that's going to be equal to x. So let's say g of f of x equals x. Now, what this is saying basically is that f and g are inverses of each other. Okay, so so we've kind of proved it the other way around. So that's what we've done, and so the inverse of f is therefore g. So if we just put down here f minus 1 of x. So we don't go. I need to go through our process of actually, reversing the order of things that we've done. We just know that from what we've done here. So f, the inverse of x is f is going to be g, which is 0.5x plus 0.75. Okay. So what is the domain and what's the range for this? Well, basically we can put any x into this, can't we? And we can put and the number we'll get out can be any number as well, because there's going to be large negative, which is going to get a very large negative number, and so on. All right, we've scaled it and we've shifted it a little bit, but essentially we're going from minus infinity to infinity. So the domain is basically the real numbers. We could write this in a number of different ways. I kind of like to write it like that. So that's a fairly straightforward example, I think, but it illustrates what we've been talking about. Okay, so hopefully that has been useful, and thanks for listening.